Welcome dear learners. We are continuing Unit 2, Chemical Bonding and Molecular Structure. In the present module, we are discussing covalent bond and coordinate bond. The contents of this module are covalent bond, energetics of covalent bond formation, polar covalent bond, non-polar covalent bond, partial ionic character of covalent bond, coordinate bond, and problems based on these concepts. First of all, covalent bond. A chemical bond formed by the sharing of an electron pair between atoms is known as covalent bond. The simplest, most common example of a molecule that contains covalent bond is our water molecule. In water molecule, there are two covalent bonds present between the two hydrogen atom and the one oxygen atom at the center. HCl is another example for a covalent molecule. H2 is a homonuclear diatomic covalent molecule. So, this covalent bond is a very popular bond among all kind of bonds. Covalent bond is formed by the mutual sharing of electrons. The electron pairs are said to be the shared pairs or bonding pairs. The stable balance of attractive and repulsive forces between atoms when they share electrons is known as the covalent bonding. Atom achieve stability by completing their octet, but for hydrogen, duet is achieved. That is, when two hydrogen combine together to produce H2, each hydrogen attain duet of configuration. That is, two electrons is filled in the outermost shell. Now, let us consider the formation of oxygen molecule. The formation of oxygen molecule happened between two oxygen atoms and there occur the sharing of two electron pair. During the formation of single bond, there will be no stability. But if a double bond formation occurs, there occur the stability and double bond is produced. Now, another covalent molecule is nitrogen. Now, let us consider its formation. The number of electron pairs shared, there are different type of covalent bonds. In a single bond, there occur the sharing of a pair of electron. For example, H2. You can see the formation of a single bond between two hydrogen atoms by the sharing of a pair of electron between the atoms. A double bond is formed by the sharing of two pair of electron. Good example is oxygen. You can see the existence of double bond, which is as a result of the share of two electron pairs here. Now, a triple bond is formed by the sharing of three electron pairs. Consider the formation of nitrogen. Each nitrogen has 5 electrons in their outer shell and each require 3 more electrons to attain octet of configuration, and hence these two nitrogen atoms share 3 electron pairs and form a triple bond between them, which leads to stability by attaining the octet of configuration. So, we heard about single bond, double bond and triple bond, which are formed by the sharing of one pair of electron, two pair of electron and three pair of electron respectively. Now, the covalent bond is formed between non-metals with comparable electronegativities. If there is considerable electronegativity between the participating atoms, for example, in the case of NaCl, one is electropositive, sodium is electropositive and chlorine is electronegative. So, there is high difference in electronegativity. The bond will not be covalent, the bond will be ionic. So, the necessary requirement is comparable electronegativity. So, comparable electronegativity is a very important requisite for the formation of covalent bond between the atoms. If the electronegativity difference is high, the bond shifted to ionic bond or more ionic character will be there. Bond strength depends on bond length and bond energy. This is the characteristic feature of covalent bond, where the strength of the covalent bond depends on two important parameters. They are bond length and bond energy. Covalent bond results in molecular compounds. Water is a molecular compound. HF is a molecular compound. Silicon carbide is a molecular compound. So, covalent bond results in the generation of various kind of molecular compounds. Covalent bond formation is exothermic. That means, whenever a covalent bond is produced between two atoms, there do occur the liberation of some amount of energy. That's why we are saying covalent bond formation is an exothermic process. This is the illustration of the fact that during the formation of a covalent bond, there occur the liberation of energy. The two circles represents two chlorine atoms. They have 7 electrons in their valence shell. When these two chlorine atoms combine together, there occur sharing of a pair of electron, and as a result of the bond formation, there occur the liberation of energy. That's why we are saying covalent bond formation and every kind of bond formation is exothermic. Moreover, you have to keep this point in your mind. Bond formation is exothermic and bond breaking is endothermic. The atoms that bonded have definite orientations relative to one another or relative to atoms participated in the bonding. That's why we are saying that covalent bonds are directional. This directional property of the covalent bond enable fixed geometries and shape for covalent molecules. For example, HCl is a linear molecule, carbon dioxide is a linear molecule, water is a bend-shaped molecule, ammonia is pyramidal, CH4 is tetrahedral, PF5 is trigonal bipyramidal, SF6 is octahedral. All these fixed geometries and shape are as a result of the directional properties of the covalent bond. Directional property is one important characteristic feature of the covalent bond. At the same time, you have to keep in mind the fact that ionic bonds are non-directional. So, covalent bonds are directional and ionic bonds are non-directional. Now, energetics of covalent bond formation. This is one of the core aspects of this module. We are focusing on energy changes which may occur during the covalent bond formation. Before proceeding into energy changes, we have to keep in mind the fact that bond formation is exothermic, that is an energy liberating process, and bond dissociation is endothermic, that means energy absorbing process. Now we are considering covalent bond formation. So, it is definitely an exothermic process, energy releasing process. Now we can enter into details of energetics of covalent bond formation. When a covalent bond formed between two atoms, energy is released because the system reaches a lower potential energy state as the electrons are shared between the nuclei, creating a more stable arrangement. You simply consider the formation of a covalent bond between two hydrogen atoms to get H2 gas. In this reaction, two hydrogen atoms connected together, there occur the formation of a covalent bond between two hydrogen atoms and the resultant molecule is H2. Look on this energy change. Delta H is negative. Delta H is negative means this reaction is exothermic. That is, energy is liberated. And the present situation has an energy liberation of 436 kilojoule per mole. This is a huge amount of energy. That means when 2 moles of hydrogen atoms combine together to produce 1 mole of H2 gas, the liberated energy will be 436 kilojoule. So, bond formation is accompanied by, especially covalent bond formation is accompanied by liberation of huge amount of energy. That is, bond formation is exothermic. The energetics of covalent bond formation can be illustrated by taking the formation of hydrogen as a representative example. Now, let us consider the energy changes in the formation of bond between two hydrogen atoms to form H2. That is, for the sake of convenience, we are saying that two hydrogen atoms connected together via a covalent bond to produce an H2. We are discussing how various forms of energy occur here, how energy variations occur during this transformation. When two hydrogen atoms come close together, some new attractive as well as repulsive forces begin to operate. So, when two hydrogen atoms are at infinite distance away, or when two hydrogen atoms are totally free from any kind of interactions, there will be no energy of interaction between them. At that situation, their potential energy can be treated as zero because these two hydrogen atoms are at infinite distance away. There is no interaction. But when these two hydrogen atoms come close together for the formation of a bond between them, some attractive forces and some repulsive forces may begin to operate. Now we are looking on what are attractive forces and what are the possible repulsive forces. Attractive forces. When two hydrogen atoms approaches each other, I just mentioned the fact that there occur the operation of some attractive forces and repulsive forces. Here we are looking on how the attractive force occur when two hydrogen atoms come close together. The attractive force may be between electron of first hydrogen atom with the nucleus of the second, or the force of attraction between electron of second hydrogen with the nucleus of first. This can be clearly illustrated by taking the formation of H2 molecule by the combination of two hydrogen atoms marked as HA and HB. These two hydrogen combine together to produce the molecule SAB, and during this formation, the electron of first hydrogen can attract by nucleus of hydrogen B. At the same time, there is another possibility. The electron of hydrogen B can be attracted by nucleus of hydrogen A. This leads it to attractive forces when hydrogen atom combine together. Now there is another possibility, that is the possibility of occurrence of repulsive force. How the repulsive force occur? The repulsive force may be the force between nuclei of two hydrogen atoms. Suppose the two hydrogen atoms are hydrogen atom A and hydrogen atom B. I have just mentioned now. Both of their nucleus are positively charged and they may repel each other. So, that create a repulsive force. There is another possibility for the repulsive force, that is the repulsive force between electrons of two hydrogen atoms, namely the HA and HB. So, when two hydrogen atoms combine together to produce H2, there occur some attractive forces and some repulsive forces. Attraction leads to stability, whereas repulsion leads to instability. So, now we are considering more about the energetics. It has been observed that the magnitude of the new attractive force is more in the molecule when compared with the repulsive force. Only this is the condition for attaining stability. If repulsive force is more than attractive force, there will never occur the bond formation. So, when H2 molecule is produced from the individual hydrogen atom, this is the condition, that is the magnitude of the new attractive force is higher than new repulsive force. As a result, the two hydrogen atoms approach each other and potential energy of the system decreases. As the two hydrogen atoms come close together more, the potential energy reaches a minimum value, and at this stage of minimum potential energy, the two hydrogen atoms bonded together to form a stable molecule with an average bond length of 0.74 angstrom. So, what actually happened at the bond length of 0.74 angstrom? This is the most important question. The two hydrogen atoms are mutually approaching together. Some new attractive forces and some new repulsive forces are also there. At a particular point where the repulsive force is minimum and attractive force is maximum, the potential energy of the system will be minimum, and at that stage bond formation occurs with an average bond length of 0.74 angstrom. If two nuclei again come more close together, that is more closer than 0.74 angstrom, then strong repulsive forces begin to dominate the attractive forces, which leads to increase in potential energy significantly. So, this is the potential energy diagram which illustrates all the concept that is we have just learned. This potential energy diagram is a plot of potential energy versus internuclear distance. Internuclear distance stands for the distance between the nucleus. This is the stage where the two hydrogen atoms are far away, and hence there is no overlap, and hence there is no attraction between them. That situation can be considered as a stage with the zero potential energy, and these two atoms come close together, and there occur some attractive as well as repulsive forces, and the potential energy decreases and reaches a minimum at this point where force of attraction has the highest value compared with the repulsive forces. Attractive forces are more, and this is the stage at which the situation of potential energy minimum, and at this minimum potential energy the bond formation takes place, and you imagine the situation if these atoms are more closer than the average bond length, then the repulsive force begin to dominate and the potential energy reaches the maximum, and that situation is the repulsion stage. So, the curve starts at a high potential energy, that is at zero potential energy, that is far apart, decreases to a minimum, and at this minimum point bond formation occurs and rises steeply again as the repulsion dominates, is the atoms are again more close together compared to their bond length. Now, polar covalent bonds. We are now focusing on polar covalent bonds. A polar covalent bond is a chemical bond that forms when two atoms with different electronegativities share electrons unequally. Suppose you are taking a covalent bond between two similar atoms, then what actually happened is the electron pair occupy the middle position. That is, electron pair is equally accessible to two atoms, if both the atoms have a similar electronegativity. However, if there is some electronegativity difference, what actually happened is the electron pair is not shared equally among the two atoms. That is, the electron pair is moving more towards the electronegative atom. That situation leads it to some partial charge separation. The resultant bond is called a polar covalent bond. Now we can have a detailed description of the polar covalent bond. You just go through this picture, you can see the covalent bond formation between hydrogen and chlorine to form HCl. Here chlorine is more electronegative, and what actually happened is the electron pair is shifted more towards the chlorine atom. As a result, it acquires a partial negative charge of delta minus, and hydrogen is associated with a partial positive charge of delta plus. Then the question arises, what is the reason for the polarity, or how the polarity is produced? The atom with higher electronegativity attracts the shared pair of electrons more strongly. This creates uneven distribution of electrons around the molecule, and this is a pictorial representation. This is a tug of war between two atoms participated in a non-polar covalent bond. One is chlorine, other is hydrogen. By the theory, the electron pair position must be at the center of these two atoms. If it is equally shared, the electron pair must be at the center position. But from this picture, it is clear that chlorine is more electronegative and powerful. As a result, the electron pairs shifted more towards the chlorine atom. So, this leads it to polar nature of the bond present in HCl, or HCl is a molecule with the polar covalent bond. Now, the atom with higher electronegativity acquires a partial negative charge, and the atom with lower electronegativity acquires a partial positive charge. So, these are some examples. Consider the case of HF. Fluorine is absolutely more electronegative than fluorine. So, electron pairs are shifted more towards the fluorine, and it is acquired a partial negative charge. Hydrogen at the same time receives a partial positive charge. So, HF is a polar covalent bond. Similarly, two polar covalent bonds are present in water molecule. You can see the oxygen at the center is more electronegative than the two hydrogen atoms at the periphery. So, these oxygen attract the electron pairs more towards itself from the two hydrogen atoms, leading to the generation of partial negative charge on oxygen and partial positive charges on the peripheral hydrogen atoms. So, water is a molecule with the polar covalent bond. HF and HCl are also molecules with the polar covalent bond. Now, the polarity of a covalent bond is influenced by several factors. The first factor is electronegativity difference. The second one is bond length. Third factor is the presence of lone pair of electron on the central atom. Another factor is hybridization. Presence of resonance structure has also some influence in the polarity of a covalent molecule. Now we are considering a new aspect, that is dipole moment and its relation with bond polarity. First of all, we have to define the concept of dipole moment. Dipole moment, abbreviated as mu, is a measurable quantity that directly relates the polarity of a bond or a molecule. It is the measure of the separation of positive and negative charges in a bond or a molecule. Dipole moment is a vector quantity which can be represented mathematically as mu is equal to q into d, where q is the magnitude of the charge, either positive charge or negative charge, and d is the distance between the charges. Theoretically, it is equal to bond length. The unit of dipole moment is dBi, since it is discovered by Peter dBi. 1 dBi is equal to 3.34 into 10 raised to minus 30 coulomb meter. You have to keep this numerical value in your mind whenever you are solving some numericals. 1 dBi is equal to 3.34 into 10 raised to minus 30 coulomb meter. Electronegativity difference creates a bond dipole with measurable dipole moment. For example, HCl has a dipole moment because chlorine has electronegativity of 3.16 is more electronegative than hydrogen with electronegativity 2.20. So, electronegativity difference between atoms creates strong polarity and hence now we are considering non-polar covalent bond. We just heard about the polar covalent bond and we are now focusing on non-polar covalent bond. A covalent bond where the electron pair is equally shared between atoms with similar electronegativities are known as non-polar covalent bond. The characteristics of non-polar covalent bonds are here. There occur symmetrical distribution of electrons. There occur no partial charges and the molecule is completely neutral. Here you cannot see partial plus or partial minus, and this molecule or this bond is associated with zero dipole moment. This is because there is no charge separation. For example, the bond in H2 is non-polar because both the hydrogen atoms have same electronegativity value of 2.2. Another example is non-polar molecules like N2, O2, Cl2, etc. I can pictorially represent the non-polar nature of H2 molecule by this tug of war notation. Here in this tug of war match, the participating atoms are same, they are equally powerful, and absolutely it is clear that the electron pair is exactly located at the position, at the center position, and equally accessible to both of the hydrogen atoms. So, this is the representation of a non-polar covalent bond. If it is a polar covalent bond like HCl, electron pair is shifted more towards the chlorine atom. Now, partial ionic character of covalent bond. A covalent bond involves the sharing of electrons between two atoms. However, if two atoms have different electronegativities, the sharing of electrons is unequal and that leads to partial ionic character of the covalent bond. When a covalent bond forms between two atoms with electronegativities, the bond exhibits polar covalent behavior with characteristics of both the covalent and ionic bonds. That is, the covalent bond is having some sort of ionic character also. Greater the electronegativity difference, greater will be the ionic character. Now we are discussing electronegativity difference and ionic character, their relation. Ionic character refers to the extent to which a bond behaves like an ionic bond rather than a covalent bond. As electronegativity difference delta chi increases, the ionic character of the bond also increases. For example, HF has higher ionic character than HCl because electronegativity difference delta chi between hydrogen and fluorine is larger when compared with the electronegativity difference between hydrogen and chlorine in HCl. So, HF has higher ionic character than HCl. That means higher the electronegativity difference, higher will be the ionic character. Now, ionic character can be estimated using an equation, or there is a relation between ionic character and electronegativity difference. This is that expression. Percentage of ionic character is given by 1 minus e raised to minus 0.25 delta chi square multiplied with 100, where delta chi represents the electronegativity difference between the participating atoms in a covalent bond. Based on this equation, it is possible to evaluate the percentage of ionic character. Higher the electronegativity difference, more will be the ionic character. As delta chi increases, the percentage of ionic character increases. This is example of ionic character based on electronegativity difference. The left hand side in the first column gives some bonds like H2, HCl, NaCl and MgO. Associated electronegativity difference are also shown in the second column. You can see the fact that if electronegativity difference is 0 as in the case of hydrogen, then percentage of ionic character will be 0. As the electronegativity difference increases, you can see a shift towards ionic character, and in the case of MgO, the electronegativity difference is very high, that is 3.5, and it is associated with the percentage ionic character of approximately 90%. Now, dipole moment and its connection with the percentage of ionic character. The percentage of ionic character is calculated by comparing observed dipole moment to the dipole moment if the bond was 100% ionic. So, the percentage of ionic character can also be calculated from the concept of dipole moment, or dipole moment is used to calculate the percentage of ionic character. This is the expression connecting percentage of ionic character and the dipole moment. Percentage of ionic character is equal to mu observed divided by mu ionic multiplied with 100. Here mu observed is the experimental value of the dipole moment or measured value of the dipole moment, and mu ionic is the theoretical dipole moment where we assume the bond as 100% ionic, which is obtained through full charge transfer. Now we are considering the coordinate bond. The coordinate bond is also called the dative bond or coordinate covalent bond, is a very important category of chemical bond, and we are now entering into the details of the coordinate bond. A bond where both the shared electrons come from the same atom is called a coordinate bond. That is, a coordinate bond is a chemical bond in which both the electrons required for the formation of a covalent bond is donated by a single atom. The atom that donates the electron is known as the donor atom, and the next atom is called the acceptor atom. Consider the formation of NH4 plus. It is clear from this picture that nitrogen atom of ammonia molecule donate both the electron for the formation of a covalent bond between nitrogen and H plus. So, nitrogen is the donor and H plus is the acceptor during the formation of NH4 plus ion. Now, the coordinate bond between NH3, that is donor atom nitrogen, and BF3, the acceptor atom boron, can be illustrated like. Now we are discussing some problems based on the concept we have learned. The first MCQ, a covalent bond between atoms is non-polar if these are the options. The bond length is short, electrons shared equally, electron negativity difference is large, one atom donate a lone pair. Your answer is option B, electrons are shared equally. This is the second MCQ. The partial ionic character in a covalent bond is due to These are the options. Option A, equal sharing of electrons. Option B, lone pair of electrons. Option C, difference in electronegativity, and option D, small atomic radii. On careful analysis of these options, you can arrive at the final answer as option C, that is difference in electronegativity. Now another MCQ. The coordinate bond is also known as, this is a very simple question. Ionic bond, hydrogen bond, dative bond and metallic bond are the options. It is very well clear that the coordinate bond is otherwise called the dative bond. So your answer is option C. Now the last multiple choice question from this topic. Which of the following has highest dipole moment? These are the options: carbon dioxide, HCl, CH4 and O2. It is very well clear that carbon dioxide is a molecule having zero dipole moment. HCl is a polar molecule. CH4 is non-polar due to its symmetric tetrahedral arrangement. O2 molecule is a diatomic molecule with a zero polarity, and hence you can arrive at the final answer as option B, that is HCl. That all about the discussion on the present module. Have a nice learning experience. Thank you.